see here. Okay. Oh, this won't work if you don't put in the dongle, will it? Fascinating. You learn something new every day. Okay. So, still logging in. Now, I know there's some folks who like to take notes off of slides, and so I'm going to try to keep the slides at least a couple of weeks posted early, so that if you want to print them out so that you can make handwritten notes on the slides, that'll be fine. Okay, so today we're going to do a little bit on you having trouble getting in?
Yeah, I don't know what my password is not working. I put it in my phone at work for you, but it doesn't work. I'll just take this one out here.
Okay, yeah, that's fine. Okay, so this is our agenda for today. We're going to do a little housekeeping, real-time kernel concepts, and going to kind of do a little bit of an intro to our development platform. So I've already introduced myself. I am co-owner of an engineering company. One thing that I will tell you about me and about our company, about 5 years ago, we made a basic policy change in the way we design software. So it is, and it's a philosophy change. And the basic rule is that if you're an engineer designing software for me, if you choose not to use a real-time operating system, you have to explain why that's a better plan. Okay? And that really came after I made a decision on a piece of software that I was writing for an embedded device, and the way the device looked, the first time that we talked to the customer about it, the first time that we defined it, it looked like, you know what, who wants to spend hours and hours, maybe 3 or 4 days worth of engineering time getting the RTOS set up on this particular little device? Yeah, there's memory for it, but this is a really simple project. Well, 2 to 3 months into this simple little project, the client started understanding what they could do, and what was simple became very complex, but it became complex slowly. So by the time that we realized that we should have done it the first time around with an RTOS, it was too late to take it back without redoing hundreds and hundreds of man-hours worth of work. And the fact is that an RTOS doesn't cost that much, even in terms of setup time anymore. So it's just not worth it to not use an RTOS. So these are some of the goals that I have for you. Those are all in the syllabus. You need to be able to talk about an RTOS. So one of the things that this class is going to do is that this is going to make you a more powerful person when you go in and interview for a job. Okay? It's just a fact. If you can go in and say, yes, I understand real-time operating systems, I've used real-time operating systems, I've used the TI RTOS, I understand a little bit about FreeRTOS and a little bit about microCOS. I understand a little bit about how Linux ties into an RTOS. And then you can demonstrate that you really do know by being able to speak the vocabulary. Holy moly. That puts you head and shoulders above most people who you're interviewing with. I've got a young man right now who's working for me as an intern. Really smart, He's a graduating senior at University of Texas at Dallas. And just as for instance, they absolutely did not cover ERTSD in his program in computer engineering. But other things they didn't really cover are using bitwise operations in C and why that might be important, or understanding the differences between, the real programming differences between a 16-bit or a 32-bit signed or unsigned value, why it's important to make those things. None of that was covered in any of his programming courses. They just gave them basic assignments and made that happen. So I will tell you, in this course, you can't just assume that, int is good enough. The other thing that you're going to learn is that float and double are evil words. Okay? About halfway through the class, near mid-semester, we're going to start talking about some techniques, because this is real time. Although we're doing RTOS, this is really real-time embedded software development is what the name of this course is, because we're going to cover most of the important stuff about an RTOS here in the first month or so, or a couple of months. But what we're going to have after that are going to be other techniques that you can use when you're writing embedded software to get better at this. And one of those things is that I will say it now and I will say it again. I don't want to see anybody using floats or doubles anywhere in their code when you are in my class, and that includes the decimal point, the period. The only excuse in the C program for an embedded project to ever use the dot is for dividing pieces of a structure or union member. Okay? Dots and numbers never ever go together, and I'll talk to you at some point in time about how that goes. So, my grading and expectations. So, as I said earlier, my expectation is the software that you are going to be writing is going to be the same level of quality that I expect out of my software engineering staff, my professionals. You guys are all juniors and seniors. You've all had several programming classes. There is no reason that you shouldn't be capable of performing at that level, and so I'm just going to tell you you will perform at that level. I experimented the last time I taught this course with doing team programming projects, and I wasn't satisfied that everybody was getting the benefit of the course out of that. It's a little more work for me to grade. We've got 16 folks enrolled in the class. A little bit more work for me to grade 16 projects when we do that, but I would rather do that and make sure that you guys all get what you need to get than have you kind of lean on whoever is the best on your team. Having said that, one of the things that I'm going to change about this course this semester is that I'm going to, it's pretty reasonable in an hour or so to get everything that I want to cover in a week covered from a lecture standpoint. So what I'm going to do is that I'm going to, and maybe this is why we really don't need to have a big monitor in here, but what I'm going to do on Mondays is that I'm going to cover as much, probably all, but if something scooches over till Wednesday, of the project, of the lecture for the week. Wednesdays, I'm going to come in here and I'm going to focus on answering questions and being interactive with you guys. Okay? So, since these don't have the tools that we need on them, I will see if we can get the tools installed, but let's pretend that that's not going to happen for the next 3 or 4 years, because it is, after all, the computer science department. Let's plan on bringing our laptops and our development platforms to class on Wednesday, because you'll be working, starting this week, you're going to be working on a homework assignment until the end of the semester, one homework assignment or another that is a programming assignment. And we will focus on this class time being about helping everybody, okay? The other thing is, and I'm just going to warn you about this because I had a guy, the first time I taught this class, try to get away with this. I have been reading people's code for a long, long time. The way you write code is very much like a fingerprint. If you take somebody else's code and change the names of the variables, change the indentation, change the comments, I'll know. Okay? This is, if you can't do the work, I'd rather have you give it the old college try than to use somebody else's work. Now, that's not to say you shouldn't help each other. You should. You should look at what somebody else does. In fact, that's the best way to learn how to program, is to look at somebody who's been successful at writing code and try to understand what they wrote and then reproduce that. But the fact is that if you reproduce it the same way that the other guy wrote it, you're never going to learn how to write it yourself. You're not going to learn how to process that data. It's not any different than writing, than creative writing. How many of y'all are any good at creative writing? Anybody? Okay, well, we're all nerds. I understand that. If you just read, this is one of those things that I discovered over time. So without bragging too much, I'm a pretty good writer. Not of nonfiction, but I'm a pretty good writer when it comes to technical writing, to writing business correspondence, that sort of stuff. And one of the things that I discovered about learning how to write in English, and unfortunately I didn't discover this in college when I could actually take advantage of the resources here and the courses that I had to take anyway. I learned this later in life. If you read a lot of different people's work and you try to understand how they wrote stuff that interested you, you can use that to teach yourself how to express yourself and your words. And it's not that you are imitating them necessarily, but you're learning from their style. Okay? You want to learn how to write a legal agreement? Read a lot of legal agreements. Okay? You want to learn how to write a specification? Read a lot of specifications, and the ones that you understand, learn from. And the ones that you don't understand, don't learn from, right? Programming is the same way. Programming is creative writing in a very real sense, okay? Now, what you're creating is kind of nerdy, but you're still being creative. And so I want you guys to learn to kind of think inside of that box. So look at each other's work, learn how they did it, and then see how that can apply to the way that you think. Because I guarantee you that none of you in this room solve problems exactly the same way. It's a guarantee. Okay, so your grade is divided into quarters. Quarter will be your midterm exam. That is going to be on eCampus, and you'll have several days to accomplish that. Your final exam also on eCampus, and you'll have a few days to accomplish that as well. I'm going to have some regular quizzes, and you'll also have these homework assignments. And those quizzes and homework assignments together will be 25% of your grade. And then at the end of the class, the last weeks, the homework assignment is going to be a embedded task that is going to require you to create at least 5 different tasks that communicate with one another. And that will be 25% of your grade as well. So, all right. So, how am I going to hold you guys accountable for writing good code? All right. So, I don't know how other professors grade code. It's not my problem. Okay? Here's how I grade code. First of all, what is it Ronald Reagan used to say, trust but verify? I trust you guys, but when you turn in a program and you tell me that it works and you turn in an executable, I have no way of really knowing from those two things whether or not the source code that you give me that looks really pretty is what actually generated that binary executable that actually works. Okay? So how do we do that? I'm going to have you guys turn in your code in such a way that I can import it into my Code Composer Studio environment, build it and load it on my reference platform that is identical to yours, and that is how I judge whether or not the program works. Okay? You don't get a D for trying in the real world. Okay? The only acceptable solution in the real world is that what you did works. Now, it turns out that sometimes there are levels of working, so there's a little room for interpretation there, but basically, a little over half of any grade on a programming assignment is always going to be, did it work? Okay? So if it didn't work, you didn't pass. Compiler warnings. I have a pet peeve about compiler warnings. Okay? Compiler warnings are there for a reason. The compiler warnings. Does anybody know why compilers throw warnings? No? Way too much to hope that any of y'all had ever actually read the C programming, the actual C standard, right? Okay. It turns out that there are some places where the C language is not defined perfectly. That there are multiple ways to interpret the standard, and that there are some subtleties about the way that code is used that can make things that look very similar act very differently in programming. So what a compiler warning is that it's saying, you know what? I see what you've done. I know what to do with this, so I'm not going to call it an error, but are you really sure that's what you want to do? I'll give you a great example with an if statement. If there's not a marker here. Fiddlesticks. You have a whiteboard, no markers. Yeah. Ah, perfect. You're wonderful. You get a B+. All right. So, let's if x, one equal sign, equals 0. That is completely legal in C. Okay? And here's what it does. It takes the constant 0, puts it into the variable x, and then looks at what it just put in the variable x and says, hey, if that's true, I'll execute this. Okay? Will it ever execute that code? Will this statement ever execute in here? How many vote yes? Okay, I got one. How many vote no? How many vote I don't have a clue? Okay. This can never execute here. If I said x equals 7, and then do if x single equal sign 0, it's going to put a 0 overriding that 7, and this will not execute because this can never be true. Now, it turns out that there's a reason that that's legal. And the reason is that C would allow you to do something like, instead of saying if x equals to 0, you might have a call to a function A that returns an int, and you might compare that to see if you put a 3 in there. That's an appropriate way to write the C code. Or you might write just this that would execute this if statement if the value that func returned was non-zero, right? Because an if is always assumed to be true if the value that it's evaluating is non-zero. So cool stuff here, right? But the compiler, if you just have the equal sign in here, is going to throw a warning. Because the odds are what you really meant to say was if x equal, which is a logical operation, 0, right? That's what you meant to say. That's why it throws a warning. The problem is that there's so many more that are extremely subtle. That's not going to, that's a simple example, but it's not the only kind of example you're going to get. So that's why I have this problem with warnings. If you have a warning, it means that you didn't understand what you wrote. Because that particular warning, so let's talk about how you fix that particular warning. If that was really what you wanted to do. So let's say if x equals 0 is really what you want to do, which I kind of doubt, right? What you can do is that you can put parentheses around the x equals and then do a double equals like that, okay? And now the compiler warning will go away, okay? So there are always ways to eliminate a compiler warning and still have your code work, okay? And so I want you to eliminate compiler warnings. If you don't eliminate the compiler warnings, I'm going to count off. This is one that it's 15% of the grade, but I'm going to tell you that it used to drive me nuts. And in fact, it really ticked me off when I took my first programming course, which was a language called Fortran, which none of y'all have probably ever heard of. Yeah. But I was self-taught. I taught myself Fortran before I took the class, and I went in. The professor actually handed out all of the assignments for the semester. This was a 101 class. Handed out all the assignments for the semester the first day of class. And I went and completed all of the assignments in the first 2 weeks of class and turned them all in. And I had several that I got bad grades on. And I was pissed because they worked. Okay? The code worked, but it wasn't demonstrating what he was trying to teach that week. Okay? So the way I'm going to ask you to solve problems may not be the way that I solve the problem with experience and having completed the class. Okay? But you have to solve it the way that I tell you to solve it because I want you to learn. I want you to show that you've learned what I've tried to teach, right? Because if you can solve it another way, but you didn't learn what I was trying to teach, you may miss something later on. So that's part of the grade as well. So design documentation and comments. I am okay if you put some of your documentation in a text file that you include with it. I am okay if you provide me with a flow chart or a state diagram or something else that tells how your code works. I am okay in this class if you do nothing but comment your code well. Okay? But I want there to be enough comments in your code and enough documentation in your code that I understand how you wrote it, why you wrote it the way that you did, and if something goes wrong, then I can understand it well enough that I might be able to change 1 or 2 lines of code and get it to do what it was supposed to do when it wasn't doing it, therefore giving you more of that 55% when the code that you turned in didn't work. Okay? So, comment your code well, include a text file that tells me where stuff is, that sort of stuff. And that's a big piece of your grade. 10% of the grade is conforming to the class coding standards. If you go on to eCampus, you can download the class coding standards. We'll talk about a few things in it today, but come on in, you're not late. It was confusing. We will be doing this all over again here in a little bit. Okay, so going to eCampus, okay? This is your homework for this week. This week, I want you to set up your homework environment on your personal computer at home, okay? If you want to follow on, you can log on to eCampus. The notes are up on the thing, or you can look over somebody's shoulder. On Monday, if you have any questions, Monday and Wednesday of next week, preferably Monday because you'll have a programming assignment on Monday. But Monday or Wednesday of next week, I want any questions that you have on the coding standards and what we meant this week, because you don't want to write a lot of code and then discover that you're not complying with the standard. Okay? So you need to read and understand that. And you are going to start on homework assignment 1, which is Blinky. Okay? And we'll cover that in more detail next week, but it is due a week from today. Reading assignment, section 1 of the TI-RTOS kernel user's guide. It's riveting. Not really. Okay. So let's start talking about some real honest-to-goodness, no kidding, real-time software development stuff. Okay? You guys have all written something for an embedded application, right? In C, and it all had a main. Okay? How many of y'all have written an embedded application, an application that controls a device, where the code ever exited main on purpose? Anybody ever done that? Do you have any idea what happens when that happens? Nobody knows what happens when that happens, because none of the compilers know what to do. Hey, he's running this code in ROM. He's done with the code in ROM. What do we do? Right? So, every program that you do in your embedded life has a while one in it someplace. Right? Or you've defined forever to be something non-zero and it says while forever, or, you know, you've done a pound define grass is green as one, so you do while grass is green. Doesn't make any difference how you do it. You're going to do this for a loop. That's called a super loop, okay? And that is a real concept that we have in embedded software development. Now, the odds are, in fact, I'm certain that you guys have written things more complicated than just a plain super loop. Some of you have written something where there are interrupts, and that's what a foreground-background system is. And then we're going to be learning how to do an RTOS. So let's take a look, first of all, at a super loop. So a super loop, the super loop example that I have on the slide, is basically 4 tasks. It executes task 1, executes task 2, executes task 3, executes task 4, executes task 1, executes task 2, executes task 3, executes task 4. Okay. And this is an example, so that you see some code there. That's an example. Come on in, don't worry, you're not late. We're going to start over for those who did exactly what I told you to. There were some other folks who did what was logical. Okay, super loops. So, and you can get on eCampus, you can pull up the slides. So, you can see this code here. Basically, what the purpose of this code is, come on in, pull up eCampus. What the purpose of this code is to read an ADD converter, write the information from the ADD converter out on the serial port. Okay? That's really what we're trying to do. So, we're going to do something to initialize the code, yeah, whatever. And then we've got this while loop. And so the while loop's pretty easy to understand. Read the ADD value, read the serial command, which may say, you know, give me a value, write the results to the serial port, and then we're going to delay so that we can read it at the same time every time. So we're not reading just as fast as we can, but we're reading once every 5-6 milliseconds. And so we've sized that for loop to be slow enough that it takes time. How many of y'all have ever done a for loop like that to do a time delay? Okay. Cool. And although there is an excuse for writing that, one of the things that I will nail you in a code review for, if you work for me, is using a timing loop ever. Now, turns out, and you can comment this if that's what if you need to do, there are some appropriate times to write a timing loop. Very few. There are also some appropriate times in C to use goto. Very few. Okay, so that's a super loop. So, super loop's really easy, right? As you know, it's all right there. I can see what's going on. It's no big deal. Don't have to pay anybody for a compiler, or I have to pay them for a compiler, but I don't have to pay anybody for an operating system. I don't have to buy any special code libraries. It just works. You don't need a lot of training, right? You did super loops first time you wrote "Hello World." It doesn't require a whole lot of memory in the processor to do those things. So, but here's the problem. So, doing a super loop, it can be really difficult to capture external events. So think about a situation where, that you might be using a super loop in, where you are waiting for somebody to press a letter on the keyboard, right? So you're waiting for something to come in over the serial port. But you're also going to go off and do something that's a few hundred milliseconds. It's entirely possible that by the time you get around to checking the serial port, not the character that you were looking for, but the character after the one that you're looking for is what's in the register, and now you're screwed because you didn't know what happened. You missed it. So that's one of the problems with a super loop, is that you can't really control that. The other thing is complexity grows really, really quickly. So this little simple thing that I just did, no big deal, right? It's really straightforward. It's ready to rock and roll. But you know what? If I make this more complicated, okay, if I start doing things like taking commands off of the serial port and changing the scale factor for the ADD port, okay, if I start changing the frequency at which I'm updating the ADD value, if I change whether I'm printing it out as binary or as hex or as decimal, all of those things, when you start adding features like that, it starts getting really, really, really complicated in a super loop. So don't worry, for those of you who are coming in later, I realize there was confusion about start time of class. I am going to redo the first part of the lecture. I just wanted to honor the folks who came in here early, who didn't none of us were clear on our communications, particularly me. Okay, timing. This is the last thing I'm going to point about a cons about super loops. Timing correctly and precisely is virtually impossible in a superloop, except for the very simplest of superloops. So, foreground background systems. Foreground background systems we have been doing since long before anybody thought that a real-time operating system was an important thing to do. And so if you take a look at the example here that I've got about a foreground background system, what you'll see is that I've got task 1 and it runs for a while, and then something happens and this interrupt routine occurs. You go off and you run whatever the code is associated with the interrupt, and then you come back to task 1. By the way, those of you who just came in, if you go to eCampus, all the slides are up there. Then you run task 2, you start task 3, oops, there's another interrupt. And we're off to the races. So, and then you do task 4, and then you come back into the loop. Now, those interrupts aren't going to occur at the same time every time in the code, right? But basically what happens is that we're running along, and we stop, and then we restart. Okay? So that's the concept of a foreground background system. So the code up here, by the way, if you log into eCampus, you can follow along on the slide since I know it's hard to see up here. So you can take a look at this foreground background system. The background stuff is your while 1, right? So you can see in this example, in the while 1, we're reading the A to D converter, we're reading a serial command, we're writing the serial result, we're going to wait for a timer flag, we'll clear the timer flag, and then we're going to do this all over again. So in the foreground, what you see is I've got this serial interrupt routine. And the serial interrupt routine, whenever there's a character coming in on the serial, it stores whatever character received. And the other foreground function that I've got is the timer interrupt service routine. And all that timer interrupt service routine does is that it wakes up, clears the interrupt, and then sets the timer flag that says, hey, we're done. Timer's timed out. So, pros and cons. By the way, foreground versus background. Background is the stuff that happens all the time. Foreground is the stuff that happens on demand. So an interrupt routine is always foreground. Background is your while loop. There will be a test question on that. Okay, so again, foreground background systems. You don't have to buy anybody's library to foreground background system, right? Not hard to learn how to do it, although there are some tricks to writing interrupt subroutines well. It's pretty straightforward still. You only have a single stack. And since you haven't done an RTOS before, you're going to say, why in the heck would you have more than one stack? We'll talk about that later, but trust me, with an RTOS, you have multiple stacks. You don't need any extra memory for storing extra stuff. And when an interrupt happens, you usually get around to servicing it very, very quickly because you're not going to be, unless you make the mistake of disabling interrupts too often, in which case, yeah, latency is a problem. Does everybody understand the term latency? Is there anybody who doesn't understand the term latency? Okay, you don't understand term latency. Nothing wrong with that. So latency is the amount of time between when an event occurs and the action associated with that event occurs. Okay? So, great example of latency. If you're sitting there at the back of the room and you throw a baseball at my face, if you throw it like that, my latency is such that I might be able to step out of the way. If you throw it overhand, you're going to break my nose because the speed of the ball is faster than my latency. Okay? And it turns out that there are lots of embedded things where latency is very important. So what's the problems with foreground background systems? So it's better to do timing than just a straight super loop, but you can still have some issues getting timing right. Everything in the background has its priority within limits of hardware implementation, right? You're not going to make servicing the timer substantially more important than servicing the serial port, because there's no way to really do that. Yes, the interrupt may happen faster, but you're still dealing with it in that super loop, and so you're still going to deal with it whenever the super loop gets around to it, as opposed to when it happened. If one function takes too long, every function suffers, right? If you have something that just takes a little bit too long, everything gets slowed down, not just one function. And it's still, as you get more complex, it can still get complex quickly, although not as bad as in a super loop situation. So let's talk about operating systems versus kernels. And this is a weird world, okay? Because we all, I included, talk about an RTOS when what we mean is a kernel. So a kernel is something that takes care of inter-task communication and timing. Who's running at which given time, which is all you really need for real-time operations. An operating system does other things. An operating system can do file systems. Windows. Windows is an operating system, right? Is it real-time? Well, we know intuitively that it's not. Okay, we'll give you some tools to understand why it's not real-time. But what does Windows do for you? So Windows has this thing called a file system that talks to this thing called a disk drive, or this thing called a flash drive, or this thing called the internet. It has this file system. It has this concept of putting a whole bunch of bits together in a thing that has a name that I can go off and I can get information out of it, right? That's an operating system concept, not a kernel concept. It has serial drivers so that you can talk to your USB port, talk to a printer, those sorts of things. It has a display driver that lets you talk to the screen, right? The operating system didn't have a display driver, you wouldn't be able to look at the slides on your computer, okay? Those are all operating system type things. So, but let's talk about, right now, let's talk about real time. We said this was not real time. What on earth does that mean? Anybody want to take a guess? So, real time is determined by a term called determinism, okay? Something that has to happen in a determined amount of time, therefore deterministic, is said to be real time. So, if Windows guaranteed that every time I press a key on the keyboard, that within 2.5 minutes, the operating system would do whatever it has to do with that key, that would be real time. Now, that's every 2.5 seconds, and it's still real time. So you can imagine, you're typing along there, right? And it takes 2.5 seconds for each keystroke. It doesn't feel like real time, okay? But it is real time because it's deterministic. Now, Windows, on the other hand, okay, Windows is like a really bad spouse. Sweetheart, take out the garbage. Okay, whatever. By the way, that's me sometimes. Is the trash going out right now? No. Okay. Is the trash going out eventually? Maybe. Okay, that's Windows. When something happens in Windows, does it happen right away? Yeah. Will it happen? Yeah, probably. Right. Except occasionally you get the blue screen to death. So real time is about having a deadline, basically. So there are two types of time tasks. Hard real-time tasks, and there are soft real-time tasks. Okay? So we'll use your car as an example. Okay, you got computer systems in your car. Okay? Anti-lock braking system. The task associated with anti-lock braking, that is a hard real-time task. Because if it is supposed to go out there and apply pressure to the brake pad, and it doesn't happen on time, you go crashing into the light pole. Okay? So that's a hard real-time task. Okay? If you have a cell phone voice response system in your car, and you say, phone, dial the office. If that doesn't happen right away, I'm annoyed, but I'm not dead. Okay? So the difference between a hard real-time task and a soft real-time task. So a hard real-time task is something that when you fail to meet that timing requirement, really severe bad things happen. A soft real-time task is a task where when you fail to meet the deadline, it's not good. People are going to be annoyed, but we're all going to live to tell about it. Okay? And a lot of times, in a lot of real-time, embedded real-time systems, a lot of times you can tolerate missing a deadline on a soft task a lot, and nobody will care. Right? So if the like the phone app, if the scheduling deadline for responding to the dialing app is half a second, and 6 times out of 12 it takes 600 milliseconds instead of 500 milliseconds, nobody cares, right? I mean, you care as the programmer because now you're starting to creep up to that area where people will start caring, but you kind of don't care. So that's soft real-time versus hard real-time. So I talked about this a little bit before. Fast software is not deterministic, okay? And it's not necessarily real-time, just because it's fast. So one of the things, a lot of times people will say, and you have this with engineers who should know better. You have an engineer say, hey, yeah, we probably need an RTOS because that's got to be really fast. Well, it turns out that that's actually a dumb statement, okay? If it's got to be really fast, maybe what you need to do is have a faster CPU, maybe. Maybe what you've got to do is that you've got to have you got to have an interrupt-driven system, you know, that will be very responsive. But fast is not, real-time operating system is not the cure for fast. And in fact, in many cases, a real-time operating system is not going to be as fast as a 4-round background system. Okay? But the real-time operating system is almost always going to be capable of achieving determinism. Now, the fact a real-time operating system does not guarantee determinism, but at least gives you the ability to design to be deterministic. So determinism is a desirable thing to do in a real-time operating system. So, and by the way, determinism doesn't mean that something happens in exactly X seconds. It means it happens in between X and Y seconds. Milliseconds, microseconds, nanoseconds, femtoseconds, whatever. So, the real-time kernel, what is that kernel? The kernel is this framework, okay? And the TI kernel that we're going to be using is muddled, okay? The kernel is married with an operating system. And it is, and I tried, is virtually impossible to untangle the kernel from the operating system. Okay, so it's kind of a jumbled mess. You will find me saying ugly things about the TI, RTOS, and kernel from time to time. That is not to say that it is a bad kernel or a bad real-time operating system. That is to say that they've made compromises to accomplish what Texas Instruments wanted to accomplish, which is to provide a real-time operating system environment and kernel environment that will span across all of their processors. As a result, they made some compromises to classical operating systems. They also chose not to use, they wanted to provide, they had customers that were asking for things that were not part of classical definitions of particular things that we talk about in operating systems. And so rather than finding ways to adapt industry language, they simply chose to abuse industry language. Okay? So you'll find that occasionally I will tell you TI calls it this, but it's not really. It's really a XYZ. Okay? And as much as I would like to gripe and say that TI is the only company in the world that does this, the fact is that everybody who produces a software product makes compromises, and how those compromises get made is based on who is running the company at the time that they make those decisions. So you'll hear me say that. Don't go off telling everybody that TI is an awful operating system, because it's not. It's a solid, cool kernel and operating system, and it works pretty darn reliably. Okay? There are lots of things that I don't like about Code Composer Studio, because when it breaks really, really bad. Somebody sent me an email this week who was trying to set up the operating environment. Which one of you guys? You're the one? Did you ever get it fixed?
I haven't.
Oh, you haven't tried yet? Okay. It is very unforgiving when you do things wrong, and it will. And it's set up in a very complex fashion, which makes it difficult to figure out what you did wrong, other than going back and starting them off from scratch. By the way, that is why it is critical when you turn in a homework assignment that you follow my instructions line by line on turning in the homework assignment. Because if I can't make it compile on my computer, that 55% of your grade is in jeopardy. Okay? So the services provided by a kernel all have to do with meeting timing requirements, and to some extent also communications between tasks, which kind of comes back to timing anyway, and you'll see that in a little bit, or as we go on. So here are the pros and cons to a real-time operating system. Number one, a real-time operating system simplifies complex stuff. Always. No exceptions. You cannot, it is not possible to walk into my office and come in with an example of something that is simpler to understand using a 4-round background system or even a super loop than it is in an RTOS. It's not possible to be more complex. And I will tell you, 9 times out of 10, it is less complex to implement something using a real-time operating system. It is straightforward. By the way, that's something that I try to use consistently. I try not to use the word easy, because easy implies quick. Easy implies you don't have to think about it, okay? Straightforward means, hey, there's a set of concrete rules that I can do every time to get from point A to point B. It is straightforward to do deterministic timing in an RTOS. Not always easy, but it's always straightforward. It is always easier to add, and I'm using the word easy here, it is always easier to add functionality to an RTOS than it is to add functionality that you didn't anticipate to any other kind of system. It's always, 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 always easier. It's always easier. The other thing that's really cool, and those of you who still have 419 and 420 to go, may, when you start your 419, 420 project, want to consider this. An RTOS makes it much easier for multiple people to work on the same piece of code, particularly in an embedded environment. Okay? So, what are some of the cons? So, first of all, there are upfront costs. Okay? Now, whether you like it or not, there's a cost to using the TI RTOS. Okay? It used to be that you had to pay a license fee that's associated with Code Composer Studio to use TI RTOS. Now they don't have that fee anymore, but there's still a cost. You're paying for it in every chip you buy from TI. You may not recognize the cost, but it's there. Because there's a lot of cost in terms of developing and maintaining a real-time operating system, or kernel. If you have to port software that's open source, how many of y'all have ever used open source software before for something? Okay. Did you have to change anything to make it work? Or did you just get the open source and compile it and not have to make any changes?
Mess with some names in the libraries, but that's it.
Okay. So you didn't do anything complex. Okay. So I will tell you that open source either works really good or it's very expensive in terms of the amount of time you have to put in, right? So if you've ever tried, one of these days you may have an opportunity to work on putting a Linux kernel onto a processor that's almost exactly the same as this other processor, okay? Somebody tells you that that's your job, run screaming, okay? It's a huge undertaking. So open source is not free. Sometimes it is, if there are no changes to make, but often it's not free. So there are costs to using a real-time kernel. The other thing is that for simple stuff, you can kind of hack your way through doing a 4-round background system or a super loop, right? You can just have in your mind what it is that you're going to do and just start typing code, right? You can't do that with an RTOS. If you simply start writing code with an RTOS, you'll get yourself into trouble every time. You have to actually sit down and decide what you're going to do before you write the code to do it. Okay? I don't believe that's a bad thing. Okay? I believe that's a very good thing. I believe designing is why you got into this, right? You don't tell people, I don't think you're going to tell people when you get out of here, yep, I'm a hacker. I got a degree from Texas A&M in electronic hacking, and I'm really good at hacking. You guys want to do that? I suspect that what you want to do is say, yeah, I'm an electronics designer. I design embedded software, I design embedded electronics, I design this, I design that, right? That's why we got into this business. Okay? And one of the things that, because it appears easy to just sit down and start typing code, it's what we think we should be doing. Okay? But what we really should be doing before we do anything is analyzing the problem and moving forward. This is one of those things where my age was an advantage to me learning how to create code. So let me tell you how I learned how to program. This is an old war story, but it tells you a little bit about how life is different, not better, but different, and how we learn different things. So back when I was a fish, the way that you wrote code was that you went to this thing called the computing center. And they had on the wall things called key punch machines. Everybody ever seen a key punch card? You know, the little beige cards with the holes in them? Okay, the way those get created is you have a thing that looks like a typewriter that has a stack of 1,000 cards in it. It pulls up one card and you start typing and it punches holes. And fortunately, it also would actually, well, most of it actually would print it in English on the top of the card as well. Because when you drop them, it's a big mess. And so what we would do is that we'd sit there and we'd write our program, one line of code per card, okay? Write our program, and then you get this stack of cards, and you go over to this thing called a card reader. And you put it in the card reader, put the thing down, press the button, it goes, reads those cards into the big computer. Then you go get a cup of coffee, because it's going to be about 5 minutes before it comes out, before whatever you did, the printout of whatever you did comes out on the other printer. If you had a syntax mistake, you got to go change the card, pull out the bad card, put in the good card, go run it over, press the button, 5 minutes, go wait, check it out, see if it happens. Okay. That's a pain in the butt, right? But the habits that you develop as a result of that is that if you have your code come back, and let's say that I had a non-trivial program, 500 cards, okay? If my program has one compiler error when it comes back with those 500 cards, I would check every line of code, including the one that had the error, right, that I fixed, but I also check every other line of code because I didn't want to have to wait again if I made another mistake, okay? Now, I will tell you what I tend to do that is different. I tend to press the button, find the first error, and knowing that often when you fix one error in C, it ripples, you know, it takes care of all the other errors. I fix the error, compile again. Fix the error, compile again. Fix the error, compile again. Am I actually thinking about what it is that I'm fixing? No. I am now, when I do that, and I'm telling you it's a bad thing, okay, because there's a compromise between the two. When I do that, I'm now letting the compiler decide how my code is supposed to work. Y'all get that? When you let the compiler decide how you want it to work, your assumption has to be that the compiler is smarter than you about this application than you are. All right? Okay? Any of y'all think that compiler is going to be able to make your application code simply by starting with main and then correcting errors until the code comes out right? Of course not. So don't hack your code. Design it. And kernels also will always consume extra memory. So let's talk about what a task is. By the way, is everybody here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think we had 16 enrolled, so we got 3 folks missing. Let your friends and neighbors know there may be some open slots. Somebody may have dropped. Okay. So, what's a task? A task is a super loop. That's really all a task is. A task is A simple function that never exits. And it has one thing to do. Okay? If you learn nothing else from me in architecting something with an operating system, learn that a task that does more than one thing is likely not well defined. Okay? Tasks should have a single function, and they should do that, and when they're not doing that, they're not working. They should stop. Every task has a priority. So the priority is, how important is this for us to accomplish our goal, which is deterministic execution of all of our code. Okay? The task doesn't really have any concept that there are other tasks going on in the CPU. Okay? The task should be written in such a way that it is basically ignorant of what else is happening. Doesn't care. So when you write a task, the beauty of this is that complex software is hard to write, right? Because now you got to think, okay, when I do this over here, it does that over there, and this, that. But with a task, the task is, I've got this one simple thing that I'm going to do. I'm going to assume that I have complete control over the CPU. I'm just going to do it. And that's the whole idea behind a task. So if you take a look at this next graphic, okay, this shows we've got 5 tasks, okay. Each one is going to have a priority, and for each task, events can happen that will stop that infinite loop for it to go off and take care of an event. But each one of those tasks thinks that it's the only one in the CPU. It doesn't know about the other tasks. It's just waiting for events to happen. Goes off, waits for an event. When the event happens, it does something, it goes back, and it waits for it to happen again. That's what tasks do. So, same example here. In a kernel-based system that is doing this A to D and printing out the A to D, basically I've got 2 tasks. I've got my A to D converter task. And what that A to D converter task is going to do, you can see the pseudocode there. While 1, I wait until it's time to do a conversion. Then I start the A to D converter. I wait until I get a signal that says the A to D conversion is complete, and I store the value. That's all it does. That's a pretty easy piece of code to understand, right? Just going off and reading it, storing the value. I have this other task, okay, that's going to read something off the serial port. And basically what it's going to do is it's going to wait until it gets a character. When it gets a character, if it's not the end of line, it's going to put the character in the buffer. If it is the end of line character, then it's going to do whatever it takes to process the command, and we're done. We're going to go off and wait again. Okay? Now, interrupt service routines. So I've got this one that's for the timer. And what happens, and so it's just get timer, it's just seeing that the timer has occurred, the timeout has occurred, and it's going to send a signal that says, hey, it's time to start a conversion. Does it start the conversion? No. It just tells the kernel, hey, anybody interested in whether or not it's time to run a conversion, you let them know I said it's okay. The analog digital converter, it's going to signal that it's completed. When that interrupt occurs, it's going to signal that, hey, if anybody is interested, I'm done. Okay? And think about post that way, this posting a signal. When you signal something, it's basically you're telling the kernel, who's kind of in charge, telling the kernel, hey, kernel, I've done it. I don't know if anybody cares, but I'm done. That's what we're doing here, okay? And then the last one you can see is a serial interrupt. And again, you get a character on the serial port. You tell somebody, hey, I got a character on the serial port. If anybody wants it, they can have it. Whatever. So there are 2 types of real-time kernels. One is a cooperative kernel, okay? And basically what this does is this relies on every task cooperating with every other task. And so what a task does in the case of a cooperative kernel is that the task, he is truly in charge of the CPU, okay? And the CPU doesn't stop letting that task run until the task says, you know, I'm done for let somebody else use the computer, I'm going to take a nap, okay? That is what a cooperative and if a task doesn't do that, right, the task in a cooperative kernel does not let somebody else use the CPU, then no other tasks get run. Okay? So the problem with a cooperative kernel is that you can make a coding mistake, and all of a sudden you have one task that is seizing all the CPU time, which means no other tasks get run, and you got to figure out which darn task it is that isn't letting anybody have any CPU time. That's a problem. So the good news about a cooperative task, or cooperative kernel, is that you and I could very easily sit down and write a cooperative kernel. I've done it a dozen times over my career when I couldn't afford to buy a regular kernel. It's straightforward to write, you know, interrupts, that sort of stuff, pretty easy to do. What's harder to do is to write what's called a preemptive kernel. And what a preemptive kernel does is that it has something called a heartbeat, or systic in the case of the TI-RTOS, they call it. And what happens is that you set this systic to do an interrupt and return power to the kernel every so often. Default with the TI-RTOS on the MSP 420, which we're using, is every millisecond. So 1,000 times a second, this timer interrupt goes off and gives control back to the kernel, and the kernel says, which tasks do I have that are ready to run, and which ones are the highest priority? And instead of returning to whichever task it interrupted, it returns to the next highest priority task to run. Which means that even if you get a task that's hogging, as long as he's not the highest priority task in the system, other tasks will get a chance to run. So a preemptive kernel is always a better plan, and almost any commercial or most open source kernels that are vetted by the community tend to be the preemptive style. So there's a graphic here on this next slide that shows you a little bit about how a cooperative kernel works. So in essence, what happens is that you're running this low priority task, an interrupt service routine occurs. It goes off, it runs the interrupt service routine, it comes back, just like it would in a foreground background system. And then whenever task 1 gets ready to let somebody else have control, it passes control back to the operating system. Operating system picks the next higher priority task. Does that make sense to everybody? Okay. So a preemptive kernel is different. And you can see what the difference is out of that when you look at the return coming off of that interrupt service routine. See how the interrupt service routine is returning to the next higher priority task that's ready instead of returning to the task that got interrupted. Does that make sense to everybody about how that works? And you can see what the advantage is, right? Now my high priority task actually gets to be a high priority in the system. Now can you imagine, let's think for a second, right? Let's go back to your 4-round background system. Can you imagine how complex your code would get if when you got an interrupt, your code had to say, hey, you know what? I got that interrupt and service that interrupt. You know, now it's more important to do this rather than what I interrupted and go back to doing that. Can you imagine how complex that would be? That's virtually impossible to implement in a 4-round background system. But you know what? In a real-time kernel, it's just what you do. So The last thing that I'm going to talk about today are task states. So there are, this is actually, the state diagram is not exactly the way that TI describes their state diagram, but in fact it is the way that it works. And these are the terms that we're going to use because they tend to be more universal for real-time kernels everywhere. So I'm flagging you to an area where TI states it a little differently. Let's talk about a dormant task first. So a dormant task is where you've written the function. You got the C code. The compiler compiled the code. It's sitting in the ROM. And the kernel does not have a clue that it's there. Okay? You haven't started it. It's not running. It's just taking up space. That's dormant. Okay? Kind of like, you think of a dormant task. You remember when you were a kid, you get those little itty-bitty sponge dinosaurs that, you know, were like this big, and you put a drop of water on them, they go, right? That's a dormant task, okay? Dormant is not taking up any room in memory, in RAM memory. It's only taking up room in ROM. It's just kind of sitting there waiting for somebody to say it's time to start, okay? That's dormant. The next level of task is a task that's ready, okay? So a task that's ready, sitting there and he's looking around and he's saying, man, I got to do. You just tell me when, Colonel. And it's effectively, ready means it's ready. It's ready to execute. There's something to do as soon as you start that function going. Okay? A task can also be running. So the kernel is now going to go through, and the kernel has this list of all of the ready tasks and all of the other tasks as well. And he's looking, the kernel's out there looking. Task 1, are you ready? No. Task 2, are you ready? No. Task 3, are you ready? Yep. Task 4, are you ready? Yep. Task 6, are you ready? Yep. Okay, who's the highest priority? Task 4. Okay, task 4, you start. That's what the kernel does. So the kernel will transfer control to the highest priority task and put them into running, the running state. Okay? Now this really applies, what I'm about to tell you, really applies only to a preemptive, really primarily to a preemptive kernel. So I'm over here and I'm my task and I'm running, I'm doing my thing, I'm moving bits around and I'm adding numbers and I'm having a great time, and then an interrupt occurs. Did I go away? No. I'm currently interrupted. Okay? So I go into this state called interrupted, and during the state called interrupted, what happens is that it's not so much that the kernel is doing something, but it's that the interrupt function is doing something, right? So I'm interrupted. Now whatever I've got that was the interrupt service routine is doing its thing. Okay? Now, what causes me to exit that is that when that interrupt service routines can do one of two things. Okay? This is where it gets a little flaky, but an interrupt service routine can just return. Okay? In which case, that task goes immediately back to running. Okay? Does not pass go, does not collect $200, doesn't give anybody else a chance to do something. Okay, so the interrupt routine could happen, do whatever it's supposed to do, and just, boom, keep the function that was running. And so now that task that I went to interrupt state just goes back to active state. But the task can also say, hey, operating system, I just changed something that you care about, okay? And when it does that, that's that path that you see going north from interrupted to ready, okay? When the ISR exits back into that ready state, what happens is that that's the ISR saying, hey, kernel, I changed something, and that will take the task that was interrupted and change it from interrupted status to ready status. Now that it's ready, all bets are off because I have no tasks that are in running state. So what's the kernel going to do? The kernel is going to go find out who is the highest priority ready task. Okay? And it's possible that that interrupt routine changed something that a higher priority task was waiting on, and now that higher priority task is the one that the kernel will restart and put into the ready mode. Does that make sense? Okay. So the last piece that we're going to talk about is pending. For those of you who have ever been or know an English wonk, okay, pend in kernels is a transitive verb, which seems wrong, but it is, because we pend on things. And what pending means is, when I pend on something, I've told the kernel, hey, look, I've gotten to this point, and now I need to know when the A to D converter is completed. Okay? So I'm going to pend on something that the kernel knows about, and the kernel knows to put me into this pending state. So when that interrupt routine occurs, the interrupt routine is going to say, hey, as part of the interrupt routine, say the interrupt routine says, hey, I just completed an A to D conversion. It's going to send that message to the kernel, completed A to D conversion. The kernel is going to say, anybody here pending that was waiting on an A to D conversion? Oh yeah, task 3 was waiting on an A to D conversion. I will make task 3 ready to run. Now, it doesn't necessarily run task 3, but it makes task 3 ready to run so that when it goes back and it reevaluates who gets the CPU next, it knows who to do that with. Does that make sense? Okay. So, that's all the information that I was going to impart today. Those of you, let's talk real quickly. First of all, questions about what we've talked about today. Yeah.
The pending and the interrupt state, that's only for preemptive kernels or majority?
So interrupted, pretty much any, if you have an interrupt, are going to happen, right? So any kernel will have interrupted, and any kernel will have pending. The difference is that you won't have the connection in a cooperative kernel. You can't go from interrupted directly to ready. Does that make sense? Because you don't exit out of an interrupt routine and then start doing something different. You always go back into what routine was running, and then there's this path, and you can see that path there too here. What do we call that path? The task preempted. In this case, if you're a cooperative kernel, you have to say preempt me if you're in a cooperative kernel. Does that make sense? Okay? Other questions? Gnarly. So those of you who came here at 8 don't have to stay. However, let's talk about time. So this is, what time is it? It's about 10 o'clock. So, I leave on Wednesdays. I leave Dallas a little bit before 6 a.m. And assuming the traffic is what I normally expect it to be, that puts me in the north garage. No, I don't want to talk to you. I hate it when my phone decides to do voice prompt and I don't want it to. It puts me in the north garage about 9 a.m. So I can be here usually as early as 9:15. Reliably, I'm here by 9:30. I'm okay if we say class time on Wednesdays is 9:15, which might put us until about 10:15 finishing. Does that work with everybody? Everybody good with that? Okay. So we'll meet here, 9:15. I will, no later than the Tuesday before, I'm going to try to have it posted a week in advance. I will have a PDF of the slides for the week published. Since we don't have a big screen here, I'll have those published. And I'll talk to those of you who came in late a little bit about how we're going to do the Monday lectures. So, everybody good? All right. So anybody who wants to see the rerun of the first part of class can stay, and those who are who would like to see if I say anything different this time, I'll keep on recording, so they'll both be on this tape, so you can review it later. The other thing is that I'm going to be using Debut, and I will won't always post them the same day, but I will always post our lectures so that you guys can do that. I've got because I've got at least one of my new employees who's auditing the class at work. They don't get credit, but they get to keep their job. So there you go. You okay with that, Abby? All right. Okay, so let's start over. Okay, here we go. Okay. Yeah.
I had a question before.
Oh, sure.
You said that you have like Launchpad.
Who walked out the door? Make sure that they know this. Okay, I'm sorry. If you don't want to buy your own Launchpad development kit, as soon as I'm done here, I'm going to walk back to my office, and I have loaners for you guys. Okay, so it's cheap. It's $33 if you want your own, but again, you got to wait for it to get here, right? So if you want to borrow one from me, we'll be done here probably in half an hour. So just swing by my office. Everybody know where my office is? I'm over in the basement of Fermier. Go down. It's the last office on your left in the basement. Take a left. Go down. When you run out of places to go, I'm there on the left. Okay? Cool. Okay. So, it's 005 is the room number. So, for those of you who are new-ish, my 9 o'clockers, I'm Mike Willie. I have a BSEE from right here at Texas A&M. I am also Chief Technical Officer of Paragon Innovations. We're a company up in Richardson, Dallas suburb, that designs embedded products for other folks. Well, that's what I do when I'm not here, which is most of the week. You guys should know I am available via email, and anytime you need me, get a hold of me. I will answer as quickly as I can. Oh, shit. I forgot to mention this in the other thing, too. I forgot to talk about eCampus. So there's a discussion board on eCampus. I better send out an announcement about this. There's a discussion board on eCampus. I would love for you guys to help each other. So here's what I'm going to do. If you post a non-trivial question about a homework assignment in particular, but about anything associated with the course, if you post a non-trivial question to the bulletin board, you will get 5 bonus points, and I will go to 105 on your score on your next homework or quiz assignment. Okay? If you answer somebody's non-trivial post with a non-trivial answer, and it doesn't have to be right. It just has to be what you sincerely believe to be right, right? okay? Because some of the things that get posted, there will be varying grades of rightness and wrongness. I'm not grading you on the accuracy of your help. I'm grading you on whether or not you're helping, right? If you post an answer, again, you will get 5 points. You will not get 10 points for answering your own question. Okay? Let's just be clear. So I've been doing this for almost 40 years. It'll be 40 years in August. And I've been doing C programming for not as long as there was a C programming language, but close. 33 years I've been programming in C. So I have, back when Usenet was a thing, which is kind of like the biggest bulletin board system in the world. Think of it as Facebook-ish before there was any, without opinion, no. Think of it a little bit like Facebook, the predecessor to Facebook, where people could post things on different subjects. I was a regular contributor to the C standard news feed, so people would have questions about C standards, and I would be one of the guys who would regularly give them the answers to what the standard actually said. So I don't know if you guys are in the habit of reading syllabi or not, but this is all covered in our syllabus. This is what we're going to do. Most important thing that I'm going to teach you to do in this class is that I'm going to give you a set of skills that if you want to write firmware for a living, will let you walk into a job interview and nail it and get the job, okay? Because I will tell you that although I believe that if you're a competent programmer, that learning how to do a real-time operating system is very straightforward to do. I think every one of you are capable of doing this and doing it well. The fact is that industry still considers people who can deal with an RTOS to be magical, okay? So if you can get in and get the job and keep the job because you know what you're doing, I've done what I intended to do with this class, okay? So there's some specific things. You're going to learn about semaphores. You're going to learn about understanding how to share memory. You're going to learn how to design a practical system. But at the end of the day, that's what I want you to do. I want you guys to be employable out of this, okay? So everything that I do is towards you becoming the kind of engineer that I would want to hire. Fair enough? So, gradings and grading expectations. And I'm basing this not on what I know about what I'm about to say, not on what I know about what the demands are for writing programs in the classes you've taken so far. I'm basing this based on what I see people's first attempts at writing code for me, or what I see as people writing for their 420 project. I'm going to put a different level of demand on you than has been put on you before in terms of the way that you write your code. Your code will be written to a professional standard, period. Okay? If it wouldn't be acceptable for me from an engineer working for me for something that I've got a client paying $145 or $150 an hour for that work, it's not acceptable in this class. Okay? And we'll talk a little bit more detail about that in just a second. Your midterm grade is going to be 25%. That will be on eCampus. For those of you who were not here when I said this, I will say it again. I have this strong belief that life is an open book test. Okay? It is really important that I understand that you can find the answers to the important questions. I don't care whether or not you've memorized them. Hell, a lot of them I haven't memorized. Okay? But I know where to go look. Okay? I want you guys to know where to go look. So, the tests that are part of this, eCampus. Okay? Programming assignments. not going to have you sit down in class without reference materials and write code. Not going to happen. But so back to your grades. 25% midterm, that'll be on eCampus. Your final will be on eCampus, and you'll have several days to do both. You're going to have quizzes and homework assignments. Okay. There are instructions on turning in homework on eCampus. Okay. You'll see why it's important, but you have to follow the instructions on turning in things on eCampus. And then finally, 25% of your grade is going to be based on a final homework assignment that you're going to have several weeks to do, and it will be a program that you write that requires 5 tasks to accomplish the goal of the program. And that'll be 25% of your grade. So let's talk about how I'm going to grade your software. Okay. You don't get a B if it doesn't work in real life. You don't get a D if it doesn't work in real life. You get an F, and you get to do it over again until it works, or they fire you and you find another job. Okay? So my standard is a little over half of your grade is based on whether or not it works. If it don't work, you don't pass. Okay? The way that we turn software in, you're going to follow the instructions, and I will load your software onto my computer. I will hit compile. I will load it onto my reference platform. If it works on my reference platform, it worked. If it doesn't compile, doesn't work on my reference platform, it didn't work, you don't get those points. Okay? Now, the fact is that if your code is well commented, if I see a particular mistake that you never were able to find, I can change the line of code and make it work. I'll probably give you partial on the 55%. Okay, you're not going to lose it all if you're pretty close. If I've had stuff turn in, though, that there was clearly no effort made at all, you don't get partial credit on that. So there's some level of partial credit at 55, but not much. Compiler warnings. When I hit compile, there better be no warnings. Okay, that's 5% of your grade. Now, if you go look on eCampus at the actual rubric, you get one warning. It's not 5% off, but there's a scale in there. But there's a reason for that. The fact is, and we had an example. I gave this example here in the earlier class, in the earlier part of the lecture. I'm going to write some code up here that is going to generate a warning. If x equals y with one equal sign, and I'm going to say x equals 5, y equals 0. Now, that will generate a compiler warning. Any idea why that will generate a compiler warning? Should be 2 equal signs, right? Or you think it should be 2 equal signs. So if y is always 0, will this code in here ever execute, no matter what x is? Never, ever. Okay? So the compiler is going to see that, and it's going to say, hey, you put an assignment here. Different compilers give the warning differently, but it's basically going to say, hey, you did an assignment when you probably meant a logical operation. Okay? Now, that's a perfectly legitimate thing to do, right? Do an assignment, and what you really wanted to know is that y might be, one of several things, and you might have wanted, if y is non-zero, let's execute this stuff, right? But the way that you do that without generating the compiler error, that you say if paren x equals y not equal to 0, okay, that's the way to write it. And now it will say, okay, I've got an assignment here, and I'm taking the result of that assignment and comparing it to 0. Now I know what to do with this, okay? The reason the compilers give warnings is because you've done something that, although it is legal, and the compiler knows exactly what it's going to do, From a language standpoint, it's not clear what your intent was, okay? And so it is critical to clear warnings. Even though your code will often work with warnings, if you don't clear the warnings, your code may be doing something that you don't anticipate. So always clear your warnings, okay? And if you don't know why a warning is happening, ask somebody, because you may learn something about the language that you can use next time, right? Proper use of highlighted techniques. I was telling folks earlier, this is one that used to aggravate the crud out of me. And I'll tell you why it aggravated me. I taught myself how to program in the 70s because there weren't very many computer courses that we could take. And so I taught myself how to write Fortran because I thought it was fun. I was weird that way. And then I found this Computer Science 101 that was the Fortran course. Well, hell, I'd already taught myself how to program in Fortran. So I took the class. And the instructor made the enormous mistake of handing out all of the homework assignments on the first day. So I went back, and the first 2 weeks of class, I did all the semester's homework assignments, and I turned them in. And I was incensed when I didn't get A's on all of my programs because they were all picked. You know why I didn't get A's? Because there were some places where I did stuff not the way that the instructor was trying to teach us, but a different way that I knew how to do that I thought was, hey, I solved the problem. What's the difference? Well, the difference is that I'm here trying to teach you particular techniques. And if you don't use the technique that I'm trying to teach you, I don't know if you've learned it. Okay? So that's a big part of your grade, is doing it the way I told you to do it. If there's another way to do it, you're welcome to do it twice and turn it in to show me how smart you are. You're welcome to bring it up in class so that everybody can get smart together. But what I grade has to be done the way that I told you to do it. Okay? Design documentation and comments. So this is about getting credit when things don't work like you expect it to, right? Comment your code well. Give me a text file, a .text file that says, this variable does this variable does that, this function does this function does that. I'll read README files. I'll read your comments. The more that there is in there, the more likely it is that I can give you extra credit when things go wrong. Okay? There may be, so here's a possibility. Let's say that you get a compiler warning, and you don't know how to fix that compiler warning, but you know for a fact that everything is doing it like it's supposed to. Okay? You can put in a comment that says, code below generates this warning. Not sure why it does it, but it does the right thing. Leave it alone. I won't count off for not doing the compiler warning, unless you just missed something absolutely trivial. But that's one of the reasons comments are important. But the other thing that's important is that I want you to get in the habit of documenting your code. Okay? That's a big part of your grade. And last but not least, on eCampus, there are coding standards. Read them, ask questions, but understand them, because 10% of your grade is whether or not you conform with the coding standards. Okay? So, homework for this week. Go into eCampus. There are instructions there on setting up your programming environment. If you don't have the reference platform set, come by my office and get one. Read, and for Monday, have questions on the coding standards and on the instructions for turning in homework. Okay? And then the homework assignment 01, which is also on eCampus, is due a week from today. Okay? Blinky. We're going to do Blinky twice, yes.
What time?
I believe, I don't know. It's on eCampus. I believe it's on eCampus. And I don't remember what I chose, but I chose it consistently for all homework assignments. So, I think I put in the syllabus a scale for for late assignments as well. What time?
9 a.m.
9 a.m.? Okay. Yeah, basically before class. Okay, because in class, we'll go over the homework assignment. It'll be a lot easier after class than it was before. Reading assignment. Download the TI User's Guide, the kernel User's Guide. Read section 1. It's a gripping story. You may want to read it 3 or 4 times. You may give copies to your friends. Don't read it when you're tired, because you'll be going to sleep before you're done. But it's important stuff, okay? It's important to do that assignment. So, who came in last? You came in last. Where was I? Do you remember?
You were already talking about foreground and background.
Okay, so we're getting close to that. Okay, so first concepts: superloops, foreground, background systems, real-time kernels. So foreground, yeah. If you're done, you're done. Foreground, background systems, and superloops. These are all different ways that you can write an embedded program. So let's talk about superloops first. Okay. Go on to your next slide. A superloop, basically, I've got a piece of code. I do task 1. After I'm done with task 1, I do task 2. After I do task 2, I do task 3, do task 4, go back, do task 1 again, right? Superloop. You've done that 100 times. While 1, right? Okay. So here is an example of some superloop code. Okay. And basically, this code is doing 2 things. It's reading commands off a serial port, and it's also reading from an A to D converter and writing out to the serial port what it read off the A to D converter. And you can see how we do that. Nothing real difficult. But you notice how we're trying to periodically read the A to D converter. You notice the way that we're doing our time delay, we're just doing a for loop with a big number and letting it count. Bump, 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 right? You guys ever done that in a piece of code? Right? Okay. So if you're working for me, you come in and you have a piece of code where you've used a timing loop to figure out, to do a time delay, I'm going to tell you to go back and do it again. There are very few. It's a non-zero set, but there are very few times when doing a timing loop is the right thing to do to get a time delay, because it's very unpredictable, right? And you don't know how long it took to do all that other stuff. There may be if statements in there that cause those different functions to take different amounts of time. It's not a very reliable way to time things, right? So, pros and cons. Superloops are really easy, okay? For very simple stuff, they're really easy. You don't have to buy anybody's compiler. You don't have to pay anybody a license fee. Everybody can do it. You don't have to have a course in it to understand how to do it. No real training. And it's kind of the minimum memory footprint, right? You don't have a lot of variables that you got to keep, that you have to worry about getting stepped on, all that stuff. It's just there. It's kind of minimalist on everything. The problem is that it's kind of minimalist on everything. So it's difficult sometimes in a superloop to catch external events. So I'll give you a great example. Let's say that we have this superloop that we just talked about. Somebody is typing in commands on a keyboard. And let's say that they're typing it in at 115 kilobaud. And let's say that you are printing out these A to D values every 150 milliseconds. Okay? There's a chance that they could type 2 characters and before you get around to reading the first character, the second character's already overwritten the UART buffer, right? Okay, that's a big problem that super loops have, is that if something happens while you're not looking, you don't know. Okay? So, and when we start doing things and you start trying to compensate for that, which means, you know, you're going to check more often, right? Now it becomes more complex. So the complexity grows really quickly with super loops, and it's virtually impossible with a super loop to get precise timing. Okay? You can get more or less timing, but you can't get precise timing. So that's why we came up with foreground background systems. And foreground background systems are what you probably have done thus far for most of your embedded life. And that is, you got an interrupt service routine that goes off and does something. So you do task 1, the interrupt happens, you go off, service the interrupt, you return, continue with task 1, do task 2, interrupt routine happens, you go service that, you return, you do your thing, right? Foreground background. So to get your terminology right, the background is the thing that you're doing in your while 1 loop. Okay? That's, in effect, your lowest priority, okay, in a foreground background system. When an interrupt occurs, that is foreground, okay? It's foreground because it's the most important stuff. It's the stuff that happens when it's supposed to happen as the stuff that happens when you get around to it. Does that make sense? So this code down here, example, taking that example that we started off with and making it into a foreground background system. And so what we're doing here is that we've got in the foreground, if I get an interrupt that says I've got a character on the serial port, it's storing the received character into a buffer, okay, and then returning. If I get a timer interrupt, then it's going to set a flag that I can use to do a timer. So that timer interrupt can occur on a regular interval, right? And that flag just gets set, you know, every so often. Now that depends on somewhere else when you're through with the flag clearing it, but we'll see how we do that in the. So that what this code does is that in my while loop, I read the A to D converter. I see if there's something on the serial port. That reads serial is going to go look in that buffer that we have, right? I'm going to write the result from the A to D converter, and then I'm going to wait for that timer flag to get set. Okay, so that background task is setting that thing, and so it sets it, which means that now it's time to go look for another A to D converter value. So wait for that to happen, and I clear that so that it's not set when I come back around. Okay, and I go off and I do it all again. That's a foreground background system. Okay, so again, no upfront cost, be cheap. You don't need a lot of training to learn how a foreground background system works, although I will tell you that you still have to think about what's going on, right? You have to think about, oh, okay, so I get this interrupt, what's happening, how do I deal with it, how do I interface that into my other stuff? So it's not as straightforward as a super loop, but you know, you don't have to do a lot of training to figure this out. You've only got a single stack. Now you're probably saying, a single stack, why would you have more than one stack? Okay, we're going to learn about that next week. But you only have a single stack. Operating systems often have multiple stacks. So that takes up memory, right? So you got some extra memory that's associated with that. But everything kind of happens in the same spot in a foreground background system, and that makes it simple and small. And latency is not a big deal, right? So were you all here when we talked about what latency means? Okay. So latency is not a big deal in a foreground background system. So that takes us up to where you guys came in, right?
Yeah.
Cool. Any questions?
For the Monday meeting?
Yes.
Is that just
Excellent. Thank you for asking, because we did talk about this. So Monday, we are going to do it at 8, but we've got a problem. This classroom is kind of is kind of a problem. I'm going to see, because I'd like to have one. I'm going to see if I can get us a big monitor in here. But let's assume I can't. It makes lecturing kind of a pain, because you're going to be looking on your screen instead of at me. It's going to be tough to, it's tough to keep the slides in sync with what I'm talking about. And so what I had been doing in the past on these Monday classes is that I had been bringing in, Dr. Morgan and I created this prop in a box thing that you can plug into the monitor, and I can see you and you can see me, and well, that, if we don't have a big monitor here, that doesn't make any sense. So what I'm going to do is I'm going to publish, I'll get it out today in an announcement. I'm going to create a Zoom meeting, and you guys will all be individually responsible for logging into the Zoom meeting from your own computers. That's the easiest to do, and so we'll do that at 8 o'clock on Mondays. Meet here at 9:15, and my intent, I'm going to do this a little differently than I did in the past. Having this in the lab is cool. Having it with a bunch of computers that don't have the RTOS and stuff installed on them is a little bit of a pain. So here's what I'm going to suggest that you do. Y'all all have your own laptops. How many of y'all do not have a laptop? Anybody? Everybody got a laptop? Okay. So you're obviously going to install the tools on your laptop. My suggestion is that on Wednesdays you come with your laptop and your reference platform. Okay. We'll cover the bulk lecture material on Mondays. Okay. On Wednesdays, we'll finish up any lecture material that we didn't finish, answer questions, and have an interactive class. So you guys are going to be working on your homework assignments, and you'll be having issues, and we'll appropriate, I'll look over your shoulder and make suggestions, and where appropriate to share it all with the class to, that it's something that we could all learn from. We'll do that. And so we'll make this more lab-like, if you will, on Wednesdays. Does that sound good?
So, just to clarify, Monday's going to be 8 to 9:15.
Yeah. Yeah.
And then you said we would meet here at
9:15 on Wednesdays.
Okay.
Yeah. You know, earlier if you want. I won't guarantee to be here until 9:15.
Yeah. I was just wondering, because
You can come whenever you want. Yeah, you can come whenever you want. And I granted, when we talked about moving the time, I was entirely my fault. I was not clear that I was going to come down early today because I wasn't sure that everybody got the word about moving. So I knew I needed to be here at 8 today, but that was why, because I get up to be able to get here reliably and have to get up, and I have to leave Dallas before 6. It's getting here at 8 o'clock was just not going to happen. And that would mean leaving Dallas at about 4:45. Not what I want to do for a full semester. Cool. All right. Well, I'm going to shut down my computer, put on my coat, head over to my office. If you guys want units, come with me. Yeah, almost came over here with just a thumb drive. That would have been even more of an issue. Okay, let's do that for now.